Hello everyone, welcome to this lecture. So, the plan for this lecture is as follows. In this lecture, we will see the definition of linear secret sharing, which is going to play a very crucial role when we later design MPC protocols. And we will see that our Samir secret sharing satisfies the linearity property. So, linear secret sharing also known as LSS is as follows. So, recall our sharing algorithm for a secret sharing scheme takes a secret S and some internal randomness from the randomness space and generates the shares, right. So, these shares are computed as some function of your secret and the internal randomness. Now, we will say that our secret sharing algorithm SH is satisfying the linearity property, or we say that the secret sharing scheme is linear if the shares are computed as some linear function of the secret and the randomness. Okay. What does that mean? It means the following: if my internal randomness is represented by the vector R1, R2, R sub L, okay, that means the internal random coins which are generated are R1, R2, RL during the execution of the sharing protocol. And if it is the case that each share Si is computed as some linear combination of the secret and the randomness, right. So, this is a linear combination or a function of secret and the randomness, right. And why it is a linear function of secret and the randomness? Because there are this publicly known linear constants which are also called as linear combiners. Okay. And your ith share can be expressed as a linear combination of the secret and the components of the randomness. So, if this is the case, then we will say that our sharing algorithm is a linear scheme. Right, that is a definition of linear secret sharing. So, now let us see some instantiations of linear secret sharing, and we will start with Samir's secret sharing. So, just to recall, this is the Samir secret sharing algorithm where all the computations are performed over a field. If S is a field element, S is a field element which you want to share as per Samir secret sharing, then we randomly pick a polynomial f of x whose constant term is S and its degree is t, and the shares are the value of this polynomial at n publicly known non-zero distinct field elements x1 to xn. Okay. So, now to see to verify whether the Samir secret sharing satisfies the linearity property, we have to verify whether each share Si can be expressed as a linear combination of the secret and the randomness, right. And to verify that, notice that S of I, the share S of I is computed by evaluating the polynomial at x equal to xi, namely wherever x is occurring I have to substitute x equal to xi, and then only I get the value of Si, right. And okay, so sorry for the typo here. Let me change this publicly known elements as alpha 1 to alpha n, because that is what I am going to use later in my MPC protocols, right. So, and my share S of I is the value of the f polynomial at x equal to alpha I, right. So, I can keep any n non-zero evaluation points, namely the values at which the shares will be computed. Earlier I called them as x1 to xn, but right now I am calling them as alpha 1 to alpha n. Sorry for this typo. Okay. So, my share S of I is computed by substituting x equal to alpha I, and if I do that, wherever x is there I substitute it by alpha I get that S of I is this value, right. So, this holds for every I equal to 1 to n. So, if you want to compute the value of S of 1, you have to substitute x equal to alpha 1. If you want to compute the share S 2, you have to substitute x equal to alpha 2 and so on. And now this can be interpreted as if my share Si is a linear function of the secret S and the randomness A1 to AT, okay, because I can interpret this alpha I raised to power 0 as some constant element Ci1 from the field. I can interpret this alpha I raised to power 1 as Ci2. I can interpret this alpha I raised to power t as some constant Ci t plus 1, right. More specifically, if I consider the vector of Shamir shares which are computed here as per the Samir secret sharing, then I can rewrite the vector S1 to Sn, the share vector, as the following. I can interpret it as the product of this row along with this matrix, and in the matrix you have various powers of alpha 1 to alpha n starting from the 0th power to the tth power. So, now you can interpret the entire process of computing Samir shares as per the Samir secret sharing scheme as follows. So, this vector S along with A1 to AT constitute the secret and the randomness, right. So, remember, as per our abstract notation of secret sharing, there is an internal randomness, that internal randomness R in Samir secret sharing scheme is this vector of coefficients for the fx polynomial, that constitutes your internal randomness, and this is your secret S, and these are my public linear combiners, okay, and hence this satisfies the definition of linearity property, right. So, each share S1 is a linear function of your secret randomness, and the linear combiners will be the first column of this matrix. S2 will be considered as a linear combination of your secret randomness and a second column of this matrix, and like that the nth share will be considered as a linear combination of your secret randomness and the nth column of this matrix, and that is why Samir secret sharing scheme satisfies the linearity property. Okay. So, now this vector, this matrix of linear combiners, this matrix has got very nice properties, and in linear algebra we have a special name for this matrix. This matrix is called as Vandermonde matrix. We will come back to the matrix again later and explore some nice properties of this Vandermonde matrix, right. So, we have shown that Samir secret sharing scheme satisfies the linearity property, and since Samir secret sharing scheme satisfies the linearity property, now we will see some very nice properties, we will see some magic, namely we will see that how it is possible to compute linear functions of secrets which are shared as per Samir secret sharing scheme without knowing the secrets, but by performing the operations on the shares themselves. So, imagine that there is some value S which is secret shared as per Samir secret sharing scheme. So, this is your vector of n comma t Shamir shares of some value S. So, imagine that the value s is not known to anyone, there was a dealer who has secret shared the value s, party 1 has the share s 1, party 2 has the share s 2, party I has the share s I, and party n has the share s n. Again let us not call this evaluation points as x I, but rather let us call them as alpha I. So, from now onwards I will assume that all the evaluations are happening at alpha 1, alpha 2 and alpha n, which are non-zero and distinct and publicly known elements from the field. So, these are our evaluation points. That means, these evaluation points are fixed once for all, and all instances of Summit secret sharing scheme will use them as the evaluation points while computing the shares. So, that means, the value s is secret shared, say by picking a random polynomial a of x whose degree was t and constant term was s, and that polynomial was evaluated at x equal to alpha 1 and gave you the share s 1, evaluated at alpha 2 gave you the share s 2 and so on. And no one knows the value of secret s, it is some value which is secret shared, and as a whole this is now a vector of n shares. I stress that no single party has this full vector, but rather component wise each party has the corresponding component of this vector. And now imagine that C is some publicly known element from S, from your field F. Okay. Everyone knows this, all the n parties knows the value of this public constant, public element C. It could be any element 0, 1, any element from the field. Now, imagine that each party locally adds the respective shares of S. No one knows the value of S, but they have shares of some unknown value S. To their respective shares, each party add the public value C. Okay. This can be done because this is a plus operation of your field. So, what I am saying is P 1 takes the value S 1 and adds the element C. In parallel, P 2 takes the value S 2 and adds the value C. In parallel, the ith party P I takes the share S I and adds the value C and so on. Now, since the field satisfies the closure property with respect to the plus operation, they will obtain the addition operation will result in another set of field elements. So, let U 1 be the result of P 1's addition, U 2 be the result of second party's addition, U I be the result of ith party's addition, and U n be the result of nth party's addition, right. Again, now this is a vector of n values. Now, the question is this vector of n values, namely U 1 to U n, is it an arbitrary vector of n field elements, or does it constitute some special property? It turns out that it is not an arbitrary vector of n field elements, but rather it has the property that it constitutes a vector of n comma t sum is shares of the element C plus S. This is because if I consider a polynomial C x, which is the constant polynomial, namely the polynomial C of x is of the form C, its constant term is C plus all other coefficients are 0, namely 0 times x, 0 times x square and like that 0 times x power t. So, I can say that C of x is a polynomial belonging to the set of all possible polynomials whose constant term is this element C and whose degree is t. I can treat this C of x as an element of that bigger set of polynomials. It is fine if the remaining coefficients apart from the constant term is 0, but it will be considered as a t degree polynomial. So, now if I consider this vector of new values u 1 to u n, I can say that they are values of the polynomial a x plus c x, call that polynomial as say r x. So, So, let R of x be the summation of A x and C x polynomial, and R of x polynomial evaluated at alpha 1 is basically S 1 plus C, which is u 1. R of alpha 2 is basically u of 2, R of alpha I is u of I, and R of alpha n is u of n. And what is the degree of R x? It is a t degree polynomial, right. So, it is a t degree polynomial, degree t. Why? Because A x is a t degree polynomial, C x is a t degree polynomial. If you add 2 t degree polynomials over a field, you still get a t degree polynomial. And what can you say about the constant term of R x? The constant term of R x will be the summation of constant term of A and the constant term of C polynomial. The constant term of the A polynomial is the value S, the constant term of the C polynomial is C. That means, I can say that R of x is one of the polynomials, okay, from the set of all possible polynomials whose constant term is S plus C and whose degree is t. And moreover, if my A of x polynomial was randomly chosen, I can say that R of x polynomial is also randomly chosen. That means, this vector of n values u 1 to u n actually lies on a random t degree polynomial whose constant term is S plus C. I stress here that no party still learns the value of S or the value of S plus C. They have just applied the operation, they have performed the operation individually on their respective shares of S and C, that is all. And as a result, now they have got a vector of, they have individually got a share of the value C plus S without even knowing the value C, without even knowing the value S. Of course, C is publicly known, right. In the same way, imagine I take another operation where parties have a shares, parties have their respective shares of some unknown value S, S1 to Sn, and suppose they lie on this t degree polynomial A of x, and now suppose I instruct every party that okay, you take your respective share of the unknown value S and multiply it with some publicly known element C, public constant C, it is known to everyone, the constant C is known to everyone. Now, if I instruct every party to do this, and now since the dot operation of the field satisfies the closure property, after performing the dot operation on their respective shares, we will again obtain a vector of field elements, where the ith component of the vector will be available with the ith party. Let us call the resultant product elements as V 1 to V n. Now, what can I say about this new vector of n values V 1 to V n? Is it an arbitrary vector of n field element, or does it constitute a special vector? Again, it turns out that it constitutes a special vector of n values, namely these vectors constitute an n comma t Samir secret sharing of the value C times S. Why so? Because A x was a polynomial of degree t and its constant term was S. Now, consider the polynomial C times A x, its degree also will be t, because you are just multiplying each coefficient of the A x polynomial by a field element, and as a result you will, the coefficient just will change, but you will still have terms from x to the power 0 to x to the power t. So, that is why its degree will be t. And what can I say about the const? So, let us call this polynomial as u of x polynomial. So, u of x polynomial is the t degree polynomial, and what can I say about the constant term of this u polynomial? The constant term of this u polynomial is c times a of z polynomial, a of 0, and a of 0 is nothing but my secret s. So, it is nothing but c times s. So, that means by multiplying their respective shares of the unknown value S with this public constant C, the parties will obtain another set of shares which will actually constitute a vector of Samir shares for the element C times S. That means, as if the value C times S has been now secret shared among the parties. And moreover, if this vector of shares for the secret S was random, if this vector is random, vector is random in the sense that if this A of x polynomial was randomly chosen from the set of all possible t degree polynomials whose constant term is S, then so is the u of x polynomial. So, if A of x polynomial was a random element from the set of all possible polynomials of degree t with constant term S, then I can claim that the polynomial u times the polynomial u x which I have, which will be the product of the C and A x polynomial, is also a random element from the set of all possible t degree polynomials whose constant term is C times S. Okay. I stress in both the operations the value of S is not revealed. Parties are not performing any interaction among themselves, they are just applying the operation locally on their shares of S. Now, let us see some another magic. Imagine that there are two independent values S and S prime which are secret shared among the parties P 1 to P n. Again let us call this alpha I here and alpha I here. Okay. That means, in both the instances the shares are computed by evaluating the sharing polynomial at the same fixed alpha 1 to alpha n. That means, for secret sharing the value S, a random polynomial of degree t whose constant term would have been A was picked, and that polynomial was evaluated at alpha 1 to alpha n, resulting in this vector of shares. And for evaluating the secret S prime, a random polynomial B of x was picked whose constant term is S prime and degree was t, and that polynomial was evaluated at alpha 1 to alpha n, resulting in this vector of shares. Now, imagine that each party adds its respective shares of S and S prime. Since the plus operation is satisfying the closure property, they will obtain another set of field elements as a whole. So, this will be now a new vector of n field elements, and now if you see closely here, this new vector of n field elements actually constitutes a set of n comma t shares, summation shares for the secret S plus S prime. This is because if I consider the polynomial A x plus V x, let us call that polynomial as V of x polynomial. Now, this V of x polynomial will have degree t, because A x is a t degree polynomial, B x is a t degree polynomial, hence its summation, their summation also will be a t degree polynomial, and the constant term of this V polynomial will be the summation of the constant terms of the A polynomial and the B polynomial, namely S and S prime, right. So, it will, so that means I can imagine as if this W 1 to W n is a vector of n values which would have been obtained if the secret S plus S prime would have been shared by picking this polynomial V of x, right. And again we get the property that if A x was randomly chosen from the set of all possible polynomials of degree t with constant term S, or B x was randomly chosen. That means, if any of these two vectors of n comma t shares, either the shares of S or the shares of S prime were random shares, random vector of shares, then I can conclude that this V of x also constitutes a set of random n share, vector of random n shares for the secret S plus S prime. because if at least one of these two polynomials a x or b x was randomly chosen, then so is the v of x polynomial. Okay. So, that means what we have seen till now is that there are certain operations, right, which can be performed over the underlying shared value without knowing them by performing the same operations on the shares themselves. Okay. Now, what about the multiplication of S and S prime? So, imagine S was secret shared and this was the vector of values, vector of shares, and S prime is also secret shared. Parties do not know the value of S, parties do not know the value of S prime, but they would like to compute shares of S times S prime. So, again based on whatever we have seen till now, you might be tempted to propose that why not let each party multiply locally its share of S and its share of S prime. So, let us do that. So, let us propose the following: each party, say party P 1 takes its share of S and its share of S prime and it multiplies them and obtain a new value, call it y 1. Similarly, P 2 it takes its share of S and its share of S prime, multiply them and it gets a value y 2 and so on. So, like that every party is doing that. Now, what can I say about the vector of this new n values? Do they constitute summate shares of the secret S times S prime? So, if I consider the product of these two polynomials a x and b x, let us call that polynomial as C of x polynomial. Now, C of x polynomial evaluated at alpha 1 will give you y 1, because C of alpha I will be equal to A of alpha I into B of alpha I. A of alpha I is Si, the ith share of the value S. B of alpha I is the ith share of S prime, namely Si prime, and as per the multiplication operation that each party has performed, this is nothing but y of I. So, that means indeed these values y 1 to y n, they lie on the polynomial C of x at x equal to alpha 1, x equal to alpha 2, x equal to alpha n, fine. But what is the degree of this C of x polynomial? The degree of this C of x polynomial is no longer t, because it is now the product of two t degree polynomials, and if I multiply two t degree polynomials, the degree of C of x becomes 2t, it is no longer t. That means, this new vector of n values, it indeed constitutes shares of S times S prime, but the degree of sharing is no longer t, but rather it is 2t. But this was not the case for the earlier operations, right. For the earlier operations, when I performed the operations on the shares, I still obtain a new vector of shares where the degree of sharing was still t, but now the degree of sharing has changed from t to 2t. What does it mean that the degree is 2t? It means that in order to reconstruct the value S times S prime, it is no longer the case that any set of t plus 1 shareholders can come together and reconstruct it, right. So, we started with a t sharing or n comma t sharing of the values. That means, for the secret S, the secret S was shared in such a way that any group of t plus 1 shareholders could come together and reconstruct the value S, because they constitute an authorized set. Similarly, the secret S prime was shared in such a way that any group of t plus 1 parties could come together and reconstruct this polynomial B of x. But now, if parties locally multiply their shares of S and S prime and obtain their shares of S time S into S prime, to reconstruct the value S into S prime, we now need 2t plus 1 or more number of shareholders to come together, and then only they can reconstruct back this polynomial C of x. If just a set of t plus 1 shareholders come together, they can no longer reconstruct it. So, let me summarize the linearity property of Samir sharing. We have seen some operations which we can perform on secret shared values, namely we have seen addition by public constants, right. So, this was the addition by public constant operation. This is the addition of two secret shared values. This was the public multiplication by a public constant, right. So, these three operations, this operation, and this operation satisfies the linearity property. That means, you started with some secret shared value and you want to either add a constant element or multiply the secret shared value with some constant element, or you want to add two unknown secret shared values. All of them can be performed locally, right. Namely, you just apply the same operation which you want to perform on the underlying shared value on the shares themselves, and you obtain the shares of the result that you would have obtained or you would have desired on the secret shared value. But when it comes to multiplying two secret shared values, that is not possible by just locally multiplying the shares of the secret shared values. So, what does it tell you, this entire set of linearity operations? So, it tells you that if you have any publicly known linear function of some shared values, then the result of that publicly known linear function can be obtained in a secret shared fashion by applying the linear function on the shares themselves. So, for instance, what I am saying here is the following: if you have a function of the following form, if say y is equal to say some constant times a plus another constant times b plus some another constant time say e and say another constant times f. If this is the case, if this is the function you want to compute, and suppose you do not want to reveal the values of a, b, e and f, the constants c1, c2, c3, c4 they are publicly known, but the values a, b, e and f they are not publicly known, but rather they are available in a secret shared fashion. That means, each party has a share of a, each party has a share of b, each party has a share of e and each party has a share of f, where the shares would have been computed by Samir secret sharing. Now, my claim is that if this is the setting given to you, then by asking each party to multiply their shares of a with c1 and multiplying their shares of b with c2 and then multiplying their shares of e with c3 and multiplying their shares of f with c4 and then adding all the resultant values, we actually will obtain a vector of n shares which constitutes a Samir secret sharing of the value y, right. That means, it is fine even if you do not know the value a, b, e and f. By performing some operations on the shares of a, b, e and f, you would have obtained shares of y. That is what is the linearity property of Samir secret sharing. It allows you to compute any linear function of secret shared values by applying the linear function on the shares themselves. Okay. So, let us see an example for this where this will be useful, and we will require this specific example later. So, here the setting is as follows: you are given d plus 1 distinct points in the 2 dimensional plane over the field. Okay. And if that is the case, then we know that there exists a unique d degree polynomial g of x passing through those d plus 1 distinct points. So, these are the d plus 1 distinct points given to you. So, there would be some curve g of x passing through this d plus 1 distinct points, which we can obtain as per the Lagrange interpolation formula. Okay. And if I expand this Lagrange interpolation formula, as we have seen in the earlier lecture, this will be the value of the ith delta polynomial. It will have all the elements except xi as its roots, and as a result it will vanish if I substitute x equal to x1, x2, xi minus 1, xi plus 1 and so on, and it will survive at x equal to xi. Now, imagine there is a new value of x, x new, which is different from all the previous x coordinates x1, x2, x of d plus 1, and I want to compute the value of this g polynomial at x equal to x new. My claim is that the value of this polynomial g at x equal to x new is a linear function of the existing y values and the existing x values. Why so? Because if this is my g polynomial, then to compute the value of this g polynomial at x equal to x new, I just have to substitute x equal to x new everywhere in all the delta polynomials. So, that is what I have done at all the delta polynomials. I have substitute x equal to x new, and now I know the value of each delta polynomial. So, if I take the first delta polynomial and there if I substitute x equal to x new, I will obtain this value multiplied with y 1, that is outside. In the second delta polynomial, if I substitute x equal to x new, I will obtain another value multiplied with y 2, and then finally, if I take the last delta polynomial, there if I substitute x equal to x new, I will obtain this value, and that has to be multiplied with y sub d plus 1. So, now if you see closely here, I can call this term whatever is there in this square bracket as C 1. This C 1 is different from this C 1. So, that is why a different font. This is a new constant, and why it is a constant? It is a constant because C 1 inverse is given, it is publicly known, and x new is given, and all the values of old x's, namely x 1 to x of d plus 1, they are also given. So, that is why the result of performing the operation inside the square bracket, whatever is the result, that will be a field element, but that will be publicly known. So, I can consider it as a constant. So, let me call it constant C 1. In the same way, whatever is there inside the d plus 1th square bracket, the result of that operation I am denoting it by C sub d plus 1, which is a constant, okay, because everything inside the d plus 1th square bracket is publicly known. And then I can imagine now that my g of x new is equal to this constant times y 1 plus second constant times y 2, and like that the d plus 1th constant times y sub d plus 1, which is precisely a form of a linear function. That means, g of x new is basically a linear function of C 1, it is a linear function of y 1 to y d plus 1, where this C 1, C 2, C sub d plus 1 are your linear combiners and they are publicly known. So, this linear combiners C 1, this fancy C 1, fancy looking C2, a fancy looking C sub d plus 1, they are the linear combiners, and sometimes they are often called as Lagrange's coefficients. Okay. So, the point here is that if you want to compute the value of G curve at x nu, that can be expressed as a linear combination of the existing values on the G polynomial. The existing values were y 1, y 2, y I, y sub d plus 1. If they are given to you, then any new point on this G curve can be expressed as a linear combination of the existing d plus 1 points on that G curve. Now, imagine a setting where you are not given the exact value of y 1, but each party is given a share of y 1 as per the Samir secret sharing. That means, the value y 1 is not available in the clear, but it is secret shared. In the same way, the value y 2 is secret shared, value y I is secret shared, and value y sub d plus 1 is also secret shared. X 1, x 2, x d plus 1, they are not secret shared, they are publicly known, but the y components, right, they are secret shared individually among the n parties. If that is the setting given to you, my claim is you can compute the value of G polynomial at x nu also in the secret shared fashion. That means, no one will learn the value of the G polynomial at x nu, but they can perform some operation on the shares of y 1, y 2, y I, y d plus 1, which will give them shares of G of x nu as per Samir secret sharing. And this is like a magic, because even without knowing the full curve G of x, in this whole process the curve G of x will not be constructed, but rather you will be magically able to compute shares of G of x nu. So, let me demonstrate that with an example here. So, I take the field Z7 where all the operations are performed, all the addition and multiplication operations are performed modulo 7. Let us consider a case where t is equal to 1, namely all the values are secret shared with degree of sharing being 1, namely all the values will be shared through a straight line, and suppose there are n parties and say these are my evaluation points for Samir secret sharing. Okay, these are my evaluation points. That means, the shares of first party for all the values in the system will be computed by evaluating the underlying straight line at alpha 1 and so on. Okay. So, you can see that I am free to choose any 4 distinct non-zero elements. I have not selected alpha 2 to be 2, I have purposely selected alpha 2 to be 3. So, the point is alpha 1, alpha 2, alpha 3, alpha 4, they can be any 4 distinct non-zero elements from this field, that is all. So, now imagine that my x 1, x 2 and x 3, they are 1, 2, 3, and say the corresponding y values are 0, 2 and 1. So, I have denoted the corresponding y values in color because they are not available with any single party, but rather the value 0, 2 and 1 they are secret shared among these 4 parties by instances of Samir secret sharing with the degree of sharing being 1. So, imagine that the value 0 is shared through the straight line 0 plus 0 z, that is a straight line equation. It is fine that the power of z is the coefficient of z is 0, that is fine, but overall this I can be interpreted as a straight line. And now this straight line evaluated at 1, 3, 4 and 5 will give you the share 0, 0, 0, 0. That means, I can imagine that this is now a vector of 4, 1 Samir shares of the value 0. In the same way, imagine that the value 2 is secret shared through this straight line, and that straight line evaluated at alpha 1, alpha 2, alpha 3, alpha 4 gives you these values, and imagine that the value 1 is shared through this straight line, and that straight line evaluated at alpha 1, alpha 2, alpha 3, alpha 4 gives you these vector of shears. That is the setting given to you. That means, if any one of these 4 parties is curious and trying to find out what is the value of y 1, y 2 and y 3, it cannot find out as per the property of Summit secret sharing, right. Now, so that means I am basically now talking about a curve passing through 1 comma 0, that means at 1 it evaluates to 0, at 2 it evaluates to 2, say this is the point, and at 3 it evaluates to 1, say some curve. I do not, so this is not the precise curve, and I now want to evaluate that curve at x equal to 0 and compute the shears of the resultant y value. So, this is my x nu, I want to compute shears of y nu, and in the whole process nothing about y 1, y 2 and y 3 should be revealed. Just somehow we want to ensure that y nu's shears are computed. So, let us call this unknown curve as g of x curve, right. So, this g of x curve is basically passing through 1 comma 0, 2 comma 2 and 3 comma 1. And now, if I apply the Lagrange interpolation, I will get this. So, this will be my delta 1 polynomial, this will be my delta 2 polynomial and this will be my delta 3 polynomial. Okay. And now, since remember all the operations are performed over field. So, it should not interpret this as dividing by the denominator, but rather you should interpret it as multiplying with the multiplicative inverse, and I am denoting these values in color because these values are not available in clear, but parties have their shares of these colored values. The uncolored values, they are publicly known. Okay. So, now if I simplify, I get that my unknown curve g of x is this. That means, my goal is to compute g of 0, that is my x nu. X nu is 0. So, value of g 0 is nothing but it is a linear combination of the existing y values, right. So, this is my y 1, y 2 and y 3, and these are my. So, this 3, 4 and 1, they constitute the Lagrange coefficient. So, this is my Lagrange coefficient C 1, Lagrange coefficient C 2, Lagrange coefficient C 3. So, I obtain the fact that g of 0 is 3 times the first y value, 4 times the second y value and 1 times the third y value, but the first y value, second y value and third y value, they are not available with any party, single party, but rather secret shared. So, I have to just apply the same linear function individually on the shares of the respective parties. I means I am asking the parties to do that. So, that means now what the first party will do? First party will take C 1, C 1 is 3. So, 3 times is 0, C 2 is 4. So, 4 times 2 and C 3 is 1. So, 1 times 1 and all the operations are performed over the field. So, it is 4 times 2 8, 8 plus 1 9, 9 modulo 2 is 9 modulo 7 is 2. So, this will be party 1's share of y nu. Same operation party P 2 will do. C 1 times its share of first y value, 2 times its share of the second y value and 1 times its share of the third y value, and it will obtain its share of the y nu value, and like that party 3 has to do, and similarly party 4 has to do. And now you can see here clearly that these 4 values actually now constitute a vector of shares for the value 2, because they lie on this polynomial 2 plus 0 z, which is a 1 degree polynomial whose constant term is 2, and this value 2 is basically the value of y nu. That means, in this whole process what I have demonstrated is even without revealing the y 1, y 2 and y 3, the parties can apply, they can compute some linear operation on their respective shares of y 1, y 2, y 3, which will give them their respective shares of y nu. With that, I end this lecture. Thank you.